Hi everyone, and welcome to another episode of This Week in Architecture, a series where we go over relevant papers in the field of computer architecture and computer engineering. So today we're going to be looking at a paper that's a little bit older, but it's really foundational in the area of GPU and GPGPU architecture. And it's this paper from Mark Gebhardt called Energy Efficient Mechanisms for Managing Thread Context in Throughput Processors. And this is a lot of people on the paper, so people from University of Texas, UIUC, NVIDIA, Stanford, and University of Virginia. So there's a couple big people on there, so you may recognize William Dolly. He's the chief scientist for NVIDIA, so this is he's on this paper as well. So let's go ahead and go to the presentation, and let's get started. So let's present F11. All right, so let's go straight into the overview. So what is this paper about? So first of all, GPUs have complicated thread schedulers because there's a lot of thread context to manage. So there's a lot of threads on a GPU. Each thread will have some amount of storage related to what it's doing. And so because we have so many threads, we've got a lot of context. And the other thing is, of course, GPUs have large register files. So every single thread will have a certain amount of registers related to it, or that it has privately. So they're not going to share registers. So one thread will have its own private registers. And because we have so many possible threads on a GPU, we've got giant register files. So what is this paper trying to do? So it's trying to exploit the fact that registers are live for only a short window. So what we mean by live is we'll create a value. That value will be used sometime in the future, and then after it's used sometime in the future, it'll never be used again. So this is basically saying that there's a pattern that the space between a value being created and the last time it's used is actually fairly short. So in order to kind of exploit this fact, they introduced this idea of a register file cache. So instead of having to do all these expensive operations, or not expensive operations, but instead of having to do all these accesses to these large register files, what if you accessed a smaller structure? So this isn't really a performance thing, it's a power saving mechanism. But then there's the problem of this register file cache. It has to be something per thread. Now the problem with that is the size is going to explode up again. So every single thread is going to have this cache, and if this cache is too big, well, that means that suddenly you're not saving much as far as space or area goes, because you just have this giant register file cache instead. So to limit the cost of this, they look at implementing something else, which is this two-level thread scheduler. And so that's where they kind of get around this issue of having this giant register file cache by instead limiting the size of it and limiting the context that they have to manage at any given point. So, background. So, of course, as a background for all GPUs exploit a fundamentally different type of parallelism than CPUs, and that's this idea of DLP versus ILP. So, GPUs exploit data level parallelism, so they have many threads that operate on different data, while CPUs tend to focus on exploiting things like instruction level parallelism, where you have tons of instructions and you pick all the ones where you can run as many as you can at the same time without any true dependencies between them. So the other thing is threads, of course, on a GPU have to be selected for execution. And this leads to about 2 megabytes, at least on the Fermi architecture, which is fairly old now. Remember, this paper is from 2011. But still, 2 megabytes of storage just for the on-chip state for all these threads. And then, of course, as another thing, accessing the large register file could potentially in the future lead to some issues with power limitations. So if we have to keep accessing these big structures in the future when we're even more power limited than they were back in 2011, well, it's going to become a problem, especially if the number of threads that we keep putting on, if the number of SMs, which are streaming multiprocessors, you can think of them kind of as cores. If you think of the number of SMs and the number of total threads you can put on a GPU increase and increase and increase, the state is just going to increase, and the amount of times we have to access these big register files is just going to increase. So we want to kind of plan for the future in that regard. So this is a basic, very rough outline of what a contemporary GPU architecture looks like. So from a very high level point of view, you have all these SMs, which are these, you can think of as cores, all connected to the L2 cache and then memory controllers past the L2. And then inside of each streaming multiprocessor, you've got your main register file that's banked 32 ways. Then you have a warp scheduler. So this is what actually picks a selection of threads to execute at any given moment. If you're unfamiliar with what a warp is just the lowest schedulable unit inside of an NVIDIA GPU. All it is it's a grouping of 32 consecutive threads that execute in lockstep. So what we mean by that is when we execute one instruction, say an add, all 32 instructions execute that same add. And so this warp scheduler takes these, it'll take these ready warps and it will send them down here to these SIMT lanes. SIMT stands for single instruction, multiple threads. And then we have things over here like our ALUs, or special functional units, our memory, and then our texture cache. So memory here is more of L1 memory, not actual DRAM. DRAM is going to be off chip. And then we have shared memory, and shared memory is a user-managed L1 cache. So in case we know exactly what data we want to access, we can instead explicitly put things into this cache, and it's not going to just get evicted like it would in a normal L1 cache. And then of course we can dig down even further, and we've got within here itself, we've got this main register file, some operand buffering before we even get to things like the ALU. So when we're reading out multiple different operands, say for a fuse multiply add operation where we say need 3 operands. So let's look at some trends, and this is really what the paper is based on. So one thing is that only a fractional portion of registers are live at any given moment. So this kind of seems to imply that maybe our register file is just too big. And there's a lot of work that's been done in this area. Now, it's not really in the scope of this paper, but it is a valid point. And some papers we'll look at later, especially on things like register file virtualization, even seek to tackle this and decrease the register file size itself. So what are some apps that kind of show this? So they found a number of graphics apps, such as some computer games, as well as some computational apps that are used a lot of times in high performance computing, that all share these same trends. And then another trend was a large portion of these values, of course, like we said earlier, are only referenced a single time in the future. And then oftentimes that reference is shortly after creation. So we'll compute something and then we'll immediately use it afterwards, and then it's done. We'll never use it again. Or maybe we'll use it twice, or maybe we'll use it 2 instructions later, but it's something along those lines. So here we've got some quantitative data that actually shows that. So here we've got the number of reads per register value. So over here we've got video simulation, image processing, some high performance computing, and then some shader applications, which are graphics. In here we see that if we look at the blue bar and the red bar combined, the blue bar stands for a value that we just compute and we never reference again. The red is one that we compute and we reference once, the green twice, and then the purple 2 or more times, or greater than 2 times rather. So we see that even between 0 and 1, about 75% or so of all values that we create are only ever used one more time. So, not a lot of reuse there. And then we see more spatially, we see the lifetimes of values that are read only once. So we take this bar, this red values that are read only a single time after being created. And we see that oftentimes they're used 1 instruction later. So that's what this blue section of the bar represents. Red is 2 instructions later, green is 3, and then purple is anything greater than 3. So if we just look at the blue, the red, and the green combined, we see that within 3 instructions, about 40% of the time, that's the max length between creation and use a lot of the times. And that's around 40% of the time. And again, this is for things that are read only once. So what does this go to show you? It shows you that oftentimes we only read things one more time, and then again, we read it pretty shortly thereafter. Okay, so let's talk about the actual design, or the actual new idea, this register file cache. So it's a fairly simple idea, and it's intuitive, and oftentimes those are some of the best ideas, because a lot of times they just work, and not only do they work, they're implementable. So the idea is we add another small cache for register file accesses to reduce the amount of times we have to access the big register file. So if we can have, a small couple entries off to the side that we can access instead of some giant structure like our main register file, we can save a lot of power. So how does allocation work? So with allocation, we just want to start pushing every single result from the thread into that register file cache. And then replacement, we can do something as simple as first in, first out. Now, why can we do things that are this simple? So we have to think back to why we're not using something like least recently used that is used a lot of times in, say, CPU caches. And the real reason is we just kind of showed the motivating reason, which is oftentimes we take a value, we create it, and we'll use it pretty much immediately after. A lot of times in CPUs with things like instruction level parallelism, you're mixing up instructions all over the place, doing out of order execution, and so you could get patterns in accesses that you've got to capture a lot for this wider window. Now, with GPUs don't have out-of-order execution. They execute instructions in order. There's no reorder buffer or anything. They're executed in order. And because of this, we don't have to do something quite as extreme as least recently used, which is going to add some overhead anyway. So we can have something as simple as basically a FIFO queue or a FIFO buffer right here that we can look into in order to do replacement. So the thing that was created latest, it gets pushed out, and the newest things are always in. So, and then with evictions, we also want to be a little bit smarter. With evictions, what happens if, say, we have something in the register file, it gets used in the register file cache, rather, and, it's time for it to exit. Maybe it's at the end of that FIFO. Maybe it's at the end of its life as first in, first out, and it's going to get replaced. Now, do we write it back to the main register file? Well, we already showed that a lot of times, things are used fairly infrequently, and a lot of times they're dead by the time they maybe need to be written back to the main register file. So instead, we can actually just use some compile time knowledge, and we can do some liveness analysis of registers to pass some hints in to say, hey, do I actually need to keep this around anymore? Or, after it exits from the register file cache, it doesn't even need to go back into the main register file because it'll never be used again. So, we don't lose out there. So let's get into the other side of things. So how do we make this actually implementable? So right now we've got, register file cache for every single thread, and it's going to take up a lot of space. So how do we decrease that space? Well, we do it through two-level scheduling. So even a 6-entry register file cache is going to be expensive. So it's going to be about 2 megabytes in Fermi just for this register file cache to store this for every single thread. So the obvious thing is, of course, just limit the amount of state you have to look at in any given moment. So here we've got some basic single level scheduling, as was common, where you have all of your warps up here. You've got the select down here that holds the state for all of these warps, and then it will pick one of these warps, whoever's ready, and go to the SIMT lanes. So how do we decrease the size of the state? Well, we need to limit the pool of threads that we, the limit of limit the pool of threads we have to store for at any given moment. So what are the two levels here? So we're going to have a level to hide low latency operations and one to hide high latency operations. So down here at these active warps, these will hide low latency operations. So we pick a subset of warps that are all ready to execute low latency instructions. So these are going to be adds, multiplies, any arithmetic operation, even shared memory operations that have fixed timing. Now, who are these pending warps? These are going to be everyone else. So the people that, just haven't been selected yet, as well as the people that maybe are waiting on accesses to main memory. So, while doing an add or multiply operation could just take a couple cycles. Same thing with doing a access to shared memory. It'll just take a couple cycles, and we know how many cycles it will be. Accesses to main memory can be really varied, especially if you have to go off chip to the DRAM. So what ends up happening is that you might be waiting for 1,000 cycles just to get a result back. And so you don't want to just be waiting there for 1,000 cycles. So you just switch them out, right? And then you get some new active warps in. So let's look at a high-level architecture of these things together. So basically, you're going to have your main register file. Then over here, you're going to have a warp scheduler with all your pending warps. A small subset of those will be down here in your active warps, and you'll only store the information for those active warps. And when you switch one of those out, you'll have to flush the context for the one that you switched out so that the new one can come in. Then, of course, you've got your register file cache, which, again, it's not a performance enhancement tool, but you can recoup some performance by, instead of having to access the big main register file, which will be kind of slow, instead access this fast, small structure, this register file cache. And then everything else is the same as far as SMPTE lanes, your special functional units, etc. And then over here, we've got what it looks like with this register file cache as a more detailed look at that explicitly. So we've got this operand buffering, and now we've got this routing, as well as accessing this register file cache to see, are we going to be getting these from the register file cache? Are we going to get these from the main register file, etc.? And we actually do that lookup if it's actually in the register file cache. We add another part to the pipeline right here, and that's this tag check. So we do a tag check into the register file cache to see if that operand is going to be in the register file cache. Okay, so let's look at some results, right? So what they do is a look at the number of entries per thread in the register file cache and the number of read accesses, write accesses, as well as some write accesses with that kind of liveness analysis for registers. And you see that you start getting diminishing returns around 6 or 7. There's kind of an inflection point here. But you see that by the time you're already at that point, you're decreasing main register file accesses by around 80%. And that's a great gain, especially if you're just having this smaller structure there. And then here you see that between video, simulation, image, and high-performance computing applications, you've got a couple high-performance computing applications that have these big gaps between referencing values that it makes. So some don't benefit at all, but a lot of them benefit, a moderate amount, around 40%. And then up here, even some benefit 100%. So you can avoid every main register file access. And a lot of these benefit around 60, 70%. And of course, green is going to be the read traffic avoided, and red, the write traffic reported. And this is for a 6-entry register file cache. And these are just a sorted list of all the applications within the video, simulation, image processing, and high-performance compute areas. So then, so how about when we mix it with the TwoLevel scheduler? So we're going to take a little bit of a hit on the amount of accesses we can avoid, and that's because we're going to have to flush the register file cache because we're swapping things in and out. We're swapping warps in and out. So we're going to pay a little bit of a hit there, but we see that even with that hit, we're still reaching around, a constant around 60% of accesses avoided for reads, and around a little more of a spread, but between around 40 and 60% of the accesses avoided, even at around only 6 entries. And this is at, you know, a huge savings in overall size of the register file cache itself, because we're having to only store for a smaller number of active warps at any given moment. And so here we've got kind of a closing figure. So this is going to be power that they save, and then the purple is going to be overall performance. So here we have 4, 6, and 8 active warps, and then the different number of entries per thread. So here we see that with 6 active warps and a 6 entry per thread register file cache, we see that we save power around, so it's normalized to 1. So we save around, this will be around 20, we save around 25 to 30% of the overall power for the register file. So that's a pretty great savings, about 25%. And then as much as even closer to 40% in some cases. And then the other very important thing to note is we're saving all this power for the register file, or from the register file, and look at the performance. The performance is still basically 1. So down here, it's probably around 90% of the normalized performance without a register file cache. And with the register file cache and around 6 or 8 active warps at a time, you're still achieving about 100% performance with this big energy savings for the register file. Now, it's important to know that this isn't overall power decreased by 25%. This is the power of register file accesses decreased by 25%. So what are some conclusions? So power is a concern in GPU scaling. We kind of know that intuitively. And we can reduce register file energy by, on average, around 36% with that 6 entry, which totals about 3.3 watts. So not a huge amount as far as total system power goes, but it is fairly significant still, especially as far as, you know, optimizing the register file for basically no cost. And then, of course, this is an easily extensible idea as far as performance goes. So if a compiler is aware about, you know, having a register file cache, it can be a little more aggressive in terms of how it plans for managing the entries that are going to be in that register file cache at any given moment. And so there's one even better note yet that shows that this is a good paper that you don't always see. So it was actually implemented. And so this is an excerpt from a tool called MaxAS, and it's a Maxwell assembler that somebody wrote. And it talks about the operand reuse cache. So it sounds pretty similar, right? Register file cache, operand reuse cache, pretty similar. So it says so let's see what it actually says. So Maxwell, however, provides something to make up for this, and at the time offers a capability to significantly reduce register bank traffic and overall chip power draw. And this is the operand reuse cache. The operand reuse cache has 8 bytes of data per source operand slot. An instruction like the fuse multiply add has 3 source operand slots. Each time you issue an instruction, there is a flag that you can specify to use to specify if each of their operands is going to be used again. So the next instruction that uses the same register is in the same operand slot, so you don't have to go to the register bank to fetch it. So this basically says exactly what it implied in the paper, that you could do compiler optimizations, and so that's what they did. So there's a .reuse flag that you can see on instructions, and this will say, go ahead and put this in the operand reuse cache, and then a later instruction will be able to access that value that's in the operand reuse cache instead of having to access the main register file. So some really great stuff there. It's always nice when you can see when an idea gets translated into reality. So that's going to do it for today. So we looked at energy efficient mechanisms for managing thread context and throughput processors. This paper again was presented in the 2011 ISCA, which is the International Symposium for Computer Architecture. And if you want more information, feel free to go to my GitHub page at github.com/coffeebeforearch, where I've got all the code for my previous series, as well as the slides for this series, This Week in Architecture. And I also make sure to link the papers that we've looked at previously as well. So as always, I'm Nick from Coffee Before Arch, and I hope you learned something and had a nice day.